Ralph Alpher did the math in 1948 and the universe confirmed it, and then the universe got all the credit. Not metaphorically, not as a complaint. As a sequence of events that happened in a specific order and produced a specific outcome that you can verify by looking at a Nobel Prize citation from 1978 and noticing whose name is not on it. The number is 2.725 Kelvin. That is the temperature of empty space right now. Not near a star, not near a galaxy. The space between things, the genuine void, the dark that fills most of what exists, is sitting at 2.725 degrees above absolute zero, and it has been falling toward that number for 13.8 billion years, and it will keep falling long after every star has gone dark, and every proton in the observable universe has quietly come apart. The cooling does not stop. There is no floor it is falling toward that it will ever reach in any time frame that contains a word like soon. It falls and falls, and the universe grows colder and emptier, and the number that describes that coldness is precise to 4 significant figures, because human beings built instruments sensitive enough to measure it, and then argued over the last decimal place with the specific intensity that people bring to arguments about things that actually matter. 2.725 Kelvin. Sit with that for a moment. Not with what it means cosmologically that comes, but with the fact of it. That we have it. That it exists as a number with decimal places rather than as a gesture at immensity. Most facts about the universe arrive as gestures. 13.8 billion years old. 93 billion light years across. Observable. Numbers so large they stop functioning as numbers and start functioning as ways of saying, beyond your comprehension, do not try. 2.725 Kelvin is not that kind of number. It is the kind of number you could write on a piece of paper and hand to someone. It is the kind of number that implies someone measured something carefully, and behind every careful measurement there is a person who first said that number should exist, and it should be approximately this, and here is the calculation that shows why. That person was Ralph Alpher. He was 22 years old. He was sitting in a small office in the physics building at George Washington University in Washington, D.C., and the year was 1948, and he was finishing his doctoral dissertation, and the calculation he was doing would turn out to be one of the most consequential calculations of the 20th century, and almost nobody who tells the story of that calculation tells it with his name at the center of it. Here is what the universe is doing right now, while you are listening to this. Every cubic centimeter of space, including the space inside this room, including the space between the molecules of whatever you are sitting on, including the space your hand is moving through, if you are moving your hand, is filled with photons. Ancient ones. Photons that have been traveling since 380,000 years after the Big Bang, when the universe cooled enough for electrons to bind to protons and space became transparent for the first time. Before that moment, the universe was a plasma, hot, dense, opaque, a fog of charged particles so thick that light could not travel through it. Then the temperature dropped to roughly 3,000 Kelvin and the fog cleared. The photons that had been trapped in that plasma were released all at once, in every direction, and they have been traveling ever since. They have not stopped. They are in this room right now. They carry the temperature of that moment stretched and cooled by 13.8 billion years of cosmic expansion, and what they carry now is 2.725 Kelvin. They are the afterglow of the moment the universe became visible. They are everywhere. They have always been everywhere. We just did not know how to hear them. Ralph Alpher knew they should be there in 1948. He did not call them the cosmic microwave background. That name came later, after other people had found them, named them, and received a Nobel Prize for the finding. What Alpher called them, in the technical language of his dissertation, was the residual radiation field produced by the conditions of the early universe. He calculated that if the universe began in a state of extreme heat and density, which is what Gamo's Big Bang model proposed, then the expansion of that universe would leave behind a thermal signature. The radiation from the initial fireball would cool as the universe expanded. It would still be present today. It would fill all of space uniformly. And based on the physics of how radiation cools during expansion, Alpher estimated with the tools available to a graduate student in 1948, which were considerable but not unlimited, that the temperature of that residual radiation today should be somewhere in the range of 5 Kelvin. He would later refine this with his colleague Robert Herman to approximately 5 degrees. The actual value is 2.725. For a back-of-envelope calculation done with 1948 data about a process that had occurred 13 billion years prior, 5 Kelvin is not wrong. 5 Kelvin is extraordinary. 5 Kelvin is the kind of answer that should have sent people running to their radio telescopes. Nobody ran. Not because the calculation was hidden, not because the paper was classified or suppressed or lost in some archival disaster. The paper was published in the Physical Review in 1948. It was available. It was cited occasionally in the years that followed. But it was not acted on. It was not treated as a prediction that demanded an experimental test. It sat in the literature with the specific patience of a correct answer that has not yet found its moment. And years passed, and then more years passed, and the moment came and went without anyone knowing it had come, and the prediction was discovered again independently, by a different group, who did not know the first prediction existed, and this time the discovery was met with the recognition that the first one never received. To understand how that happened, you have to understand something about how the paper was written. Or more precisely, you have to understand something about whose name was on it. George Gamow was one of the most colorful figures in 20th century physics. He was Ukrainian-born, Soviet-defected, enormously energetic, famous for his popular science books, and for a sense of humor that was either charming or exhausting depending on where you stood in relation to it. He was Ralph Alpher's doctoral advisor. He was the one who had proposed the Big Bang nucleosynthesis model that Alpher's dissertation was testing and extending. He was, in the legitimate sense, the intellectual architect of the framework within which Alpher did the calculation. And when the paper was submitted for publication, the paper summarizing the key results of Alpher's dissertation, the paper containing the temperature prediction, Gamow added a name, not because that person had contributed to the paper, not because that person had read it or commented on it or had any involvement whatsoever in the work it described. Gamow added the name of Hans Bethe, a physicist at Cornell, a future Nobel laureate, a man who had nothing to do with Big Bang nucleosynthesis, because the authors' names would then read Alpher, Bethe, Gamow, and that sounded like alpha, beta, gamma, and Gamow found this funny. He did not ask Alpher's permission. He submitted the paper. Alpher found out when the paper appeared in print. Hans Bethe, to his credit, was mildly embarrassed by this. He said later that he had not contributed to the paper and that his name should not have been on it. But the paper was published. The citation exists. It has been cited thousands of times as the Alpha Bethe Gamow paper, the alphabetical paper, the Alpha Beta Gamma paper, and every time someone tells the story of the joke they are, without meaning to, repeating an erasure. Because the joke was not equally distributed. Gamow was the senior figure. Bethe was the interloper. Alpher was the graduate student whose dissertation this was, whose mathematics this was, whose calculation produced the prediction, and his name came first alphabetically, not because he was the most important contributor, but because the joke required the Greek alphabet to go in order. His actual contribution, the specific, unglamorous, mathematically intensive labor of computing what the early universe must have looked like, and what it must have left behind, disappeared into a punchline. Alpher spent the rest of his career explaining that the joke was not his. There is a particular texture to that kind of professional situation. It is not dramatic. It does not arrive as a crisis. It arrives as a recurring small correction that you make in seminars and in interviews and in conversations at conferences. And every time you make it, you are reminding the person you are talking to that your most significant work is primarily known as someone else's joke. And after a while, the correction itself becomes a kind of association Alpher, the one who explains the Alpha Bethe Gamow paper, and you realize that the explanation has become as much a part of your identity as the work itself. That is a specific kind of cost. It does not show up in any accounting of scientific progress. It shows up in a career, in a posture, in the specific way a man gives an interview and chooses his words. But the name on the paper was not the only cost. The other cost was institutional, and it was larger, and it accumulated silently over decades. After completing his doctorate, Ralph Alpher took a position at the General Electric Research Laboratory in Schenectady, New York. This was not a disgrace. GE's research division was a serious scientific institution that employed serious scientists. But it was not a university. It did not have graduate students. It did not have the structure that produces the kind of ongoing intellectual community that keeps a researcher's ideas alive, and circulating students who carry your framework into their own work. Postdocs who cite you in their first papers, colleagues at other institutions who come through on sabbatical and take your ideas back with them when they go. Universities are not just places where science happens. They are the mechanism by which scientific reputations propagate. Alpher was outside that mechanism. He continued working on the prediction. He and his GE colleague Robert Herman refined the temperature estimate several times through the early 1950s. They wrote more papers. They calculated more carefully. They attended conferences and gave talks. And at conferences, and in review articles, and in the informal conversations that actually determine what a field considers important, the Big Bang nucleosynthesis work was increasingly discussed in terms of Gamows' framework, Gamows' model, Gamows' prediction, Gamows' Big Bang, and the specific contribution of the graduate student who had done the calculation was compressed into the background radiation of someone else's reputation. This is not a story about malice. That is the important thing to hold on to. Gamow was not conspiring against Alpher. The field was not organizing itself to suppress a correct answer. What was happening was something more ordinary and more durable than conspiracy, the natural behavior of a scientific community that propagates ideas through institutions and authority and reputation, and that consequently tends to attach ideas to the most prestigious name in the vicinity of the idea, regardless of who actually produced it. Gamow was more famous than Alpher. Gamow was funnier. Gamow wrote popular books that people actually read. When someone needed to summarize Big Bang cosmology in a paragraph, they reached for Gamow. And behind Gamow, compressing further with each summary, was Alpher. Meanwhile, in 1964 in Holmdel, New Jersey, two radio astronomers at Bell Telephone Laboratories named Arno Penzias and Robert Wilson were trying to calibrate a horn-shaped antenna they had inherited from an earlier satellite communication project. The antenna was 20 feet across, shaped like a giant ear bent toward the sky, and Penzias and Wilson had plans to use it for radio astronomy, clean, precise observations of the Milky Way. Nothing exotic. Before they could do that, they needed to account for every source of noise in the system. They needed the instrument to be quiet when it should be quiet. It was not quiet. There was a noise. A persistent, low-level hiss that appeared in every direction they pointed the antenna. Not stronger toward the galactic center. Not stronger toward any known radio source. The same in every direction. They checked the electronics. They checked the amplifiers. They recalibrated the receivers. They found a pair of pigeons that had nested inside the horn, and this is in the lab records, written in the flat language of technical documentation, removed them and cleaned the interior of the antenna, removing what the records describe as a white dielectric material. This is a precise and accurate description of pigeon droppings in the language of engineering. The pigeons were relocated. The white dielectric material was removed. The noise remained. They could not explain it. What Penzias and Wilson did not know, what they had no particular reason to know, because it had not been a major topic of discussion in their corner of radio astronomy, was that a group at Princeton University, led by Robert Dick, had recently figured out that if the Big Bang had occurred, there should be a residual radiation filling all of space, and it should be detectable by a sensitive enough radio antenna, and it should look exactly like a uniform noise coming from every direction, with no identifiable source. Dick's group was in the process of building an instrument to find it. They were weeks away from beginning observations. Penzias and Wilson had already found it. They just did not know what it was. The story of how they found out has been told many times, always with a certain pleasure, because it has the structure of a comedy, the two groups close enough to call each other on the telephone, the instant recognition on Dick's end, the quiet acknowledgement that he had been beaten to the finding he had spent months preparing to make. Dick hung up the phone and told his colleagues, "We've been scooped." The two papers were published simultaneously in the Astrophysical Journal in 1965, one by Penzias and Wilson presenting the observation, one by Dick's group explaining what the observation meant. The observation paper said almost nothing about the Big Bang. It described a noise. It reported its temperature. It noted that it was uniform. The explanation was in the companion paper. What neither paper said in any prominent way was that the explanation had already been published 17 years earlier by Ralph Alpher and Robert Herman in a paper in the Physical Review, with a predicted temperature that was in the right range, based on a calculation that Alpher had done as a graduate student while Gamow was adding names to papers as jokes. This is the specific omission that every other treatment of this story soft pedals or skips entirely. It is not that Alpher and Herman went completely unmentioned, they were cited, eventually, in some of the subsequent literature. It is that the shape of the narrative that formed around the discovery did not include them as protagonists. The story that solidified the story that got told in physics departments and popular books, and eventually in the Nobel citation, was the story of accidental discovery. Penzias and Wilson, hunting for noise, found the echo of the Big Bang. Elegant, surprising, a gift from an unglamorous problem. That story is true. It is also incomplete in a way that the incompleteness costs someone something specific. To understand the full cost, you have to go back further. You have to go back to 1948 and understand not just what Alpher predicted, but what he predicted it from. Because the calculation is not simple, and its complexity is part of why it matters that a 22-year-old graduate student was the one who did it. George Gamow's Big Bang model proposed that the universe began in a state of extreme density and temperature, what he called the ilum, a word borrowed from medieval philosophy meaning primordial matter. In the ilum, neutrons were the fundamental building blocks. As the universe expanded and cooled, these neutrons would begin to combine into heavier elements through a rapid process of nuclear reactions. This was Gamow's nucleosynthesis hypothesis, that the elements we see around us today were forged in the first minutes of the universe. Alpher's dissertation was the mathematical investigation of whether this was actually true. He worked out the rate equations. He calculated the neutron capture cross-sections. He built a numerical model of how the composition of the early universe would evolve as it expanded and cooled and the nuclear reactions proceeded. This was not a back-of-envelope calculation. This was a doctoral dissertation of several hundred pages, completed in the era before computers existed in any form that could assist with the integration of differential equations, which meant Alpher was doing the numerical calculations by hand, on paper, with a mechanical calculator, working through the rate equations step by step. It took the better part of 2 years. And in the course of working through the thermodynamics of the expanding early universe, figuring out the temperature at each moment, as the expansion proceeded, Alpher derived the relationship between the temperature of the radiation field and the age of the universe. That relationship, extrapolated to the present age of the universe, gave a temperature. 5 Kelvin, approximately 5 degrees above absolute zero. He published this. He talked about it. He and Robert Herman spent the early 1950s urging radio astronomers to look for it. And here is where the specific texture of what happened becomes important, because the response they received was not outright rejection. It was something more dispiriting. The radio astronomers they spoke to said they did not have instruments sensitive enough to detect a signal at that temperature. This was true. The technology did not yet exist. But what Alpher and Herman were asking for was not an immediate detection. They were asking for the field to hold on to the prediction, to keep it in mind as a target when technology improved, to treat it as a scientific priority. And the field did not do that. The prediction did not enter the list of things radio astronomers were trying to find. It drifted. It became a theoretical curiosity associated with a cosmological model that many physicists in the 1950s were not convinced was correct. The steady-state model, which proposed that the universe had always existed and always would, that it was not expanding from a hot, dense beginning, but was continuously creating new matter to fill the gaps left by its expansion, was a serious competitor to the Big Bang in the 1950s, championed by Fred Hoyle, Hermann Bondi, and Thomas Gold. In that intellectual climate, predictions derived from the Big Bang model were not widely treated as urgent experimental priorities. Alpher and Hermann were working in an environment where the theory their calculation depended on was contested, their institution gave them no amplification, and the technology to test the prediction did not exist. They were right. They were also, in the specific way that being right without recognition differs from being wrong, invisible. Robert Dick's group at Princeton rediscovered the prediction in the early 1960s independently. Dick had been thinking about a different problem: an oscillating universe, whether the universe might collapse and re-expand in a cycle, and had worked out for himself that such a universe would be bathed in residual radiation from its previous cycles. He assigned 2 of his graduate students to build a small radio receiver that could detect radiation at the relevant frequencies and look for the signal. This was in 1964. His students were Peter Roll and David Wilkinson. They were building the instrument. They were weeks from starting observations when the phone rang. Penzias was on the line, describing a noise they could not explain. Dick knew immediately what the noise was. He had derived it himself. He had assigned students to find it. The students had not yet found it because they had not yet built the instrument to look. Penzias and Wilson had stumbled into it with an instrument they were using for something else, pointed in a direction they happened to be pointing, on a day they happened to be calibrating. The fact that Dick had also independently re-derived the prediction 16 years after Alpher and Hermann had derived it tells you something about the state of the literature. Dick was a careful, thorough physicist at one of the most prestigious universities in the world, with full access to every journal and review article in existence. He did not know about Alpher and Hermann's prediction when he made his own. He had read widely. He had not read the Alpher-Hermann papers, or had not retained them as relevant, or had seen references to them in the context of the wider GAMO nucleosynthesis debate, and filed them under a framework he was not specifically working within. This is how scientific literature works at its worst and its most ordinary, not through suppression, but through the filtering effect of reputation, institution, and framing. The Alpher-Hermann prediction was in the literature. It was accessible. It was not in the mental model of the people who needed it. The gap between those two things is not a scandal. It is a structural feature of how knowledge moves, and it is a feature that has costs, and the costs are not evenly distributed. Penzias and Wilson published their observation in the Astrophysical Journal in July 1965. Their paper was 3 pages long. It reported a temperature of approximately 3.5 Kelvin, which was later refined to 2.725 as instruments improved, and the measurement was made more precise. They noted in their acknowledgments that the interpretation of the signal had been provided by Dick's group, whose companion paper in the same journal explained that what Penzias and Wilson had detected was the cosmic microwave background radiation, the afterglow of the Big Bang. The companion paper cited GAMO. It did not prominently cite Alpher and Hermann. In the years that followed, the cosmic microwave background became one of the central pillars of modern cosmology. Every cosmology textbook published after 1965 included it. The temperature became a fundamental constant. Research groups around the world began building instruments to measure it more precisely, to map its uniformity, to look for the tiny variations in temperature across the sky that would eventually reveal the seeds of all the structure in the observable universe, every galaxy, every cluster of galaxies, every filament and void in the cosmic web, all of it encoded in temperature fluctuations of 100,000th of a degree, in a field of radiation that Alpher had predicted in 1948. Careers were built on it. The instrumentation improved decade by decade. The maps became more detailed. The physics became more refined. A scientific legacy of extraordinary richness and consequence grew from the ground that Alpher had been the first to stand on. And Alpher was at the General Electric Research Laboratory in Schenectady, doing good work, writing papers, being a careful and rigorous scientist, watching the field that had grown from his calculation become one of the most productive and celebrated in physics, and occasionally giving interviews in which he was asked how he felt about it. He was careful in interviews. He was precise. He gave credit where credit was due, which he did with a specificity that suggested he had thought carefully about where credit was and was not due. He acknowledged that Penzias and Wilson had made a genuine discovery they had. He acknowledged that Dick's group had independently worked out the theoretical basis they had. He did not claim, ever, that anyone had deliberately wronged him. What he said, in various formulations across various interviews over the decades, was something closer to: the prediction was made, it was in the literature, it was not followed up on, and the people who made the observation were not aware of the prediction. He said this without visible anger. He said it with a precision that was its own kind of feeling, the precision of a man who has rehearsed the statement for long enough that it has become the statement he makes instead of the statement he would otherwise make. Robert Herman, Alpher's closest collaborator, was less contained. Herman spent years writing and talking about the failure of the cosmological community to properly acknowledge the prediction. He was explicit about it in a way that Alpher was not, perhaps because Alpher was the one whose name was on the original paper and who would be most exposed if the complaint came across as grievance rather than historical record. Herman said clearly, in print, that the community had made an error, not a moral error, but a historical error, in assigning credit for the prediction to the wrong people. He wrote about it in a collaborative memoir with Alpher in the 1993 book Genesis of the Big Bang. He wrote about it in individual papers. He was, by the end of his career, somewhat consumed by it. Herman died in 1997. Alpher survived him by 10 years. What you notice if you read the interviews Alpher gave in the years after Herman's death is that something changed in how he talked about the prediction. He had spent decades deferring to precision, the careful, exact account of what happened, stripped of affect. After Herman was gone, there is occasionally something else. Not anger, something more like tiredness. The tiredness of a man who has been explaining the same thing for 50 years and has watched the explanation not change the record. In 2005, Alpher received the National Medal of Science. The citation acknowledged his prediction of the cosmic microwave background. He was 80 years old. He had made the prediction 57 years earlier. He died 2 years later, in 2007, in Austin, Texas, where he had retired after his years at GE and a later position at Union College in Schenectady. He did not receive a Nobel Prize. The Nobel Prize in Physics for 1978 was awarded jointly to Piotr Kapitsa for his work in low-temperature physics, and to Arno Penzias and Robert Wilson for their discovery of the cosmic microwave background radiation. The Nobel Committee's presentation speech acknowledged that the radiation had been predicted theoretically before it was observed, and named Gamow as the predictor. Alpher's name was not in the presentation speech. Herman's name was not in the presentation speech. Alpher was 63 years old in 1978. Gamow had died in 1968. He was 64 years old. He died of liver disease in Boulder, Colorado, where he had been a professor at the University of Colorado since 1956. He never knew that the prediction had been confirmed by Penzias and Wilson, or rather, he knew in the way you can know something has been found, without yet knowing whether the world will agree that you found it first. Gamow had seen the 1965 papers. He had written about them enthusiastically. He had asserted that his group had predicted the radiation. The Nobel Prize came 10 years after his death, and the Nobel is not awarded posthumously. That is a rule, not a judgment, and it applied to Gamow with a specific neutrality that cannot be called fair or unfair. But Alpher was alive. Alpher was alive in 1978 and alive in 1980. and alive in 1990, and alive in 2000, and alive when the Wilkinson microwave anisotropy probe DUMAP was launched in 2001 to produce the most detailed map of the cosmic microwave background yet made. The probe was named after David Wilkinson, one of Dick's original students who had been building the instrument in 1964 when Penzias and Wilson's phone call arrived. Wilkinson had devoted his career to mapping the background radiation. He died in 2002, 1 year after the launch of the probe that bore his name. Alpher was alive to see this. There is no way to say that cleanly. There is no way to describe a man outliving everyone around him who is being honored for work he did first, without that description carrying a weight that is either too much or not enough. Alpher did not, in any interview or writing, make this comparison. He would not have. The precision he maintained would not have permitted it. But the facts are the facts, and they have their own weight regardless of whether anyone states it. Now here is what happens to the 2.725 Kelvin. It is falling, not quickly, not in any time frame that contains a human life or a civilization or a species or a planet or a solar system. But it is falling, and the falling is not a metaphor and not a tendency and not an approximation. It is a direct consequence of the expansion of the universe, which is itself a consequence of the initial conditions of the Big Bang, which Alpher's dissertation modeled in 1948. The temperature of the cosmic microwave background is inversely proportional to the scale factor of the universe, which is a technical way of saying that as the universe gets bigger, the radiation gets colder. When the universe was 1,000 times smaller than it is now, the background radiation was 1,000 times hotter. When the universe becomes 1,000 times bigger than it is now, the background radiation will be 1,000 times colder. The universe is expanding, therefore the number is falling. By how much, right now, in a human lifetime? The universe is expanding at approximately 70 kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light-years. The expansion rate implies that the temperature is decreasing by approximately 2.3 times 10 to the minus negative 18 Kelvin per second. This is a number so small that writing it out requires scientific notation, and even then it does not feel real. It means that in an entire human lifetime of 80 years, roughly 2.5 billion seconds, the temperature of the background radiation decreases by about 6 times 10 to the negative 9 Kelvin, 6 billionths of a degree. In a lifetime, the number is falling, but it is falling the way a continent drifts at speeds that make the word falling feel almost dishonest, because falling implies a speed you can feel, and this cannot be felt. But it is happening, and the fact that it is happening, and that we know the rate at which it is happening, and that we can write down the equation that governs the rate, and that the equation was first derived by a graduate student at George Washington University in 1948, these facts are connected. The temperature of the universe and the story of the man who first predicted it are not two separate things. They are the same story. The number is what the calculation found. The calculation is what the man did. The man is what the story erased. Let's go back to the physics, because the physics itself is stranger than it usually gets described, and the strangeness is part of what makes Alpher's calculation so remarkable. When we say the cosmic microwave background is at 2.725 Kelvin, we are saying something specific about the nature of that radiation. It is not just cold. It is cold in a particular way, in a way that has a name in physics, which is a blackbody spectrum. A blackbody is an idealized object that absorbs all radiation falling on it, and emits radiation based only on its temperature, not based on what it is made of, not based on its shape or composition, only on its temperature. The radiation it emits follows a precise mathematical curve called the Planck distribution, named after Max Planck, who derived it in 1900 in one of the founding acts of quantum mechanics. If you measure the amount of energy in the cosmic microwave background at every frequency and plot it against frequency, you get a curve, and that curve matches the Planck distribution for a blackbody at 2.725 Kelvin, with a precision that is, In the words of the scientists who measured it most carefully, essentially perfect. This is not trivial. It is in fact extraordinary. The reason it is extraordinary is that the cosmic microwave background is not a black body in any physical sense. It is not an object. It is a field of radiation filling space. A perfect blackbody spectrum implies that the radiation has had time to come to thermal equilibrium, to reach a state where energy has been distributed uniformly across all frequencies according to the laws of thermodynamics. In the early universe, when the plasma was dense and hot, and photons were constantly being absorbed and re-emitted by charged particles, there was time for this equilibrium to be reached. The radiation achieved a perfect blackbody spectrum in the first year of the universe's existence. Then the universe expanded. The plasma cooled. The electrons combined with protons and the photons were released. But the spectrum, the shape of the curve, was preserved. The photons stretched to longer wavelengths as the universe expanded, and every wavelength stretched by the same factor, and the shape of the Planck curve was maintained as the temperature dropped. What we see today, 2.725 Kelvin, perfect blackbody, is a fossil of that early thermal equilibrium. It is 13.8 billion years old. It is the oldest light in the universe. It has been traveling unimpeded for longer than the Earth has existed, and when it arrives in our instruments, it traces a curve so perfect that the instruments themselves have to be tested against it to verify they are working correctly. The precision of the measurement matters because of what it took to achieve it. The first measurement by Penzias and Wilson in 1965 gave approximately 3.5 Kelvin. Subsequent measurements through the 1960s and 70s refined this, and by the early 1980s the temperature was known to be approximately 2.7 Kelvin, with uncertainty in the second decimal place. The measurements were limited by the instruments and by the atmosphere. Water vapor in the Earth's atmosphere absorbs and emits microwave radiation, which contaminates ground-based measurements. To get a truly precise measurement, you needed to get above the atmosphere. The Cosmic Background Explorer satellite COBE was launched in November 1989. It was built by NASA and had been in development for over a decade. Its primary instrument for measuring the spectrum of the background radiation was called the Far Infrared Absolute Spectrophotometer FIRAS, and it was built by a team led by John Mather at NASA's Goddard Space Flight Center. FIRAS measured the spectrum of the cosmic microwave background from above the atmosphere over the full sky at multiple frequencies and compared it to an internal black-body calibration source. The results were announced at a meeting of the American Astronomical Society in January 1990. John Mather showed the plot. The plot showed the observed spectrum, the energy of the cosmic microwave background at each frequency, as measured by FIRAS, and it showed the theoretical curve, the Planck distribution for a blackbody at 2.725 Kelvin. The two curves were, for all practical purposes, identical. The error bars on the data points were smaller than the thickness of the line on the plot. The agreement between observation and theory was so perfect that when Mather showed the plot, the audience stood up. Not at the end of the talk, in the middle of it. While the plot was on the screen, physicists at a scientific conference stood up spontaneously and applauded a graph. This is not normal behavior at scientific conferences. What they were responding to was not just a confirmation of a theory. They were responding to precision, to the demonstration that a quantity as fundamental as the temperature of the universe could be pinned down to 4 significant figures, that the universe was that well behaved, that the physics going back to the first seconds of time was that consistent and that clean. The standing ovation was for the decimal places. Alfred was alive in January 1990. He was 65 years old. He was at Union College in Schenectady at the time, having moved there from GE. I do not know whether he was in the room at the AS meeting when Mather showed the plot. I have not been able to find a record of his presence or absence at that specific event. What I know is that he was alive, and that the measurement that produced the standing ovation was the confirmation, with 4 significant figures, of the number he had first estimated 42 years earlier in a doctoral dissertation that most of the people in that room had never read. The precision of COBE was followed by even greater precision. The Wilkinson Microwave Anisotropy Probe, launched in 2001, measured not just the temperature, but the tiny variations in temperature across the sky fluctuations at the level of 1 part in 100,000 that encode the distribution of matter in the early universe. These fluctuations are the seeds of everything. The slight overdensities in the primordial plasma that became, over billions of years, the galaxies and clusters and filaments we see today. MAP produced a full sky map of these fluctuations, a portrait of the universe as it was 380,000 years after the Big Bang, painted in temperature differences measured to the millionth of a degree. The map matched the predictions of the standard cosmological model with a precision that allowed cosmologists to determine the age of the universe, the composition of the universe, and the geometry of the universe with uncertainties of a few percent. And then the Planck satellite, launched in 2009 by the European Space Agency, named after Max Planck, whose distribution describes the spectrum of the radiation, produced an even finer map. The Planck mission measured the temperature of the cosmic microwave background as 2.7255 Kelvin, 5 significant figures. The value that Alpher estimated in 1948, with the tools available to a graduate student doing hand calculations in Washington, D.C., was 5 Kelvin. 60 years of increasingly precise measurement had refined the answer from 5 to 2.7255. The original estimate was off by roughly a factor of 2. In the context of estimating the temperature left over from the first seconds of the universe, using 1948 nuclear physics data, without the benefit of any actual measurement of the quantity being estimated, being off by a factor of 2 is not an error. It is an achievement. I want to stay with this for a moment, because the precision is doing something specific to the story. When we say the temperature of the universe is 2.7255 Kelvin, we are saying that space has been measured, not observed vaguely, not estimated or modeled or inferred from indirect evidence. Measured, the same way you measure the temperature of a room with an instrument calibrated against a standard, at multiple locations, with quantified uncertainty. The universe has a temperature the way a room has a temperature, except that the room is 13.8 billion light-years across in every direction, and the thermometer is a satellite. We have put a number on the void. We have put decimal places on the nothing between galaxies. We have taken the temperature of the afterglow of creation, and it is 2.7255 Kelvin, and it is falling. The falling is what Alpher's calculation describes. The rate of cooling is governed by the Friedmann equations, the equations of general relativity applied to the universe as a whole, derived by the Russian mathematician Alexander Friedmann in 1922 from Einstein's field equations. The Friedmann equations describe how the scale factor of the universe, which you can think of as a single number, that describes how big the universe is at any given moment, relative to some reference size changes over time, as a function of the matter and energy content of the universe. As the scale factor increases, the temperature of the background radiation decreases in proportion. The equation connecting temperature and scale factor is clean and exact. Temperature times scale factor equals a constant. As the universe expands, the constant stays constant, and the temperature falls. What this means concretely is that the universe has a thermal history that is as determinate as a cooling cup of coffee, except that the universe will never finish cooling. A cup of coffee reaches room temperature and stays there. The cosmic microwave background has no floor. It falls toward absolute zero along a curve that is perfectly described by the physics, never reaching zero, never stopping. In the far future, not the distant future, not the remote future, but the genuinely incomprehensible future. The future measured in googles of years, the temperature of the background radiation will fall below the temperature of the Hawking radiation emitted by the last black holes as they evaporate. When that happens, even the radiation from black holes will be warmer than the background radiation of space. The universe will have passed through a kind of thermal inversion, a moment when the last dying remnants of matter are the warmest things in existence, and space itself is colder than anything that has ever been measured in a laboratory. That future is a long way off. But the direction is fixed. The number only moves one way. And the number is 2.7255 Kelvin right now, which means it will be 2.7255 Kelvin minus something very small in 1 second, and minus something slightly larger after a year, and minus something larger still after 1,000,000 years, and the subtraction never stops. The universe is getting colder every second. This is not a dramatic statement. It is not a metaphor for entropy or decay or the heat death that popular science sometimes invokes when it wants to sound ominous. It is a measurement. It is a calculation. It is what the physics says. The universe is getting colder every second, and the number that proves it is 2.7255 Kelvin, and the person who first calculated that that number should exist was a 22-year-old graduate student in Washington, D.C., and his name was Ralph Alpher. Let's talk about what the number actually is. Not what it represents cosmologically, what it is physically, what it means to say that space has a temperature at all, because this is one of those things that sounds straightforward until you look at it directly and it becomes strange. Temperature, in the physics sense, is a measure of the average kinetic energy of particles in a system. The temperature of a gas is related to how fast its molecules are moving. Hot gas has fast molecules. Cold gas has slow molecules. Absolute 00 Kelvin is the temperature at which particles have the minimum possible energy, at which they are as still as quantum mechanics permits them to be. You cannot go below absolute zero. There is no such thing as negative absolute temperature in this sense. The temperature scale has a floor, and the universe is 2.7255 Kelvin above it. But space is not a gas. Space between galaxies contains on average less than 1 atom per cubic meter. It is not empty in the quantum mechanical sense. The vacuum is a seething background of virtual particles and quantum fields, and the zero-point energy of every field in the standard model, but for the purposes of temperature in the macroscopic sense, it is as close to nothing as anything in the observable universe gets. So what does it mean to say that this near nothing has a temperature? What it means is that space is filled with photons. The cosmic microwave background photons, the ones released when the universe became transparent, are everywhere, all the time, passing through everything. Roughly 411 of them per cubic centimeter. This is not an estimate or an average, it is a derived quantity from the measured temperature. Using the formula for the number density of photons in a blackbody radiation field. 411 photons per cubic centimeter, filling all of space, carrying the temperature 2.7255 Kelvin, which is to say carrying the energy of a blackbody at that temperature, distributed across wavelengths that peak in the microwave range wavelengths of a few millimeters, frequencies of a few hundred gigahertz. These photons are passing through you right now. They are not dangerous. Their energy is far too low to ionize atoms or cause biological harm. They pass through the atmosphere, through walls, through bodies, through the Earth itself. They are not quite ghosts because they interact weakly with matter. A metal conductor will reflect them, which is why the COBE and MAP and Planck satellites needed to be carefully shielded from the Earth's own microwave emissions. But they pass through you. 13.8 billion years of travel, from the moment the universe became transparent, through the expansion that stretched their wavelengths from visible light to microwave, across a distance so large that the source of the light no longer exists in any meaningful sense, and they are in this room, passing through everything in it, including you. The temperature of the cosmic microwave background is the temperature of this radiation field. When we say the universe is 2.7255 Kelvin, we are saying that these photons carry that energy, that they fit that curve, that if you built a thermometer sensitive to microwaves and pointed it at the sky at any part of the sky, it would read 2.7255 Kelvin, and then it would read a number infinitesimally smaller, and then smaller again. Because the photons are still stretching, the universe is still expanding, the wavelengths are still growing, the temperature is still falling. There is a consequence of this falling that is strange enough to deserve its own moment. As the temperature of the cosmic microwave background falls, it will eventually fall below the temperature of what are called relic neutrinos, the neutrino background, which is a similar relic from an even earlier epoch, when the universe was hot enough for neutrino reactions to be in equilibrium with the electromagnetic plasma. The cosmic neutrino background is estimated to be at a temperature of 1.95 Kelvin right now, colder than the photon background, because neutrinos decoupled earlier, when the universe was hotter and smaller, and have been cooling since then relative to the photon background. As the universe expands, both backgrounds cool, but they cool at slightly different rates because of the way electrons and positrons annihilated in the early universe and transferred energy to the photons but not the neutrinos. The photon background is warmer than the neutrino background by a factor of the cube root of 11/4, raised to the 1/3 power, a factor that comes directly from the thermodynamics of the early universe and has been verified by cosmological observations. The point is that the universe has multiple thermal backgrounds, multiple layers of residual radiation from different epochs, cooling at different rates, all moving toward the same zero that they will never reach. The universe is not a single cooling object. It is a set of overlapping cooling processes, each with its own temperature, each with its own history, each falling toward the same floor from a different starting height. Ralph Alpher's calculation addressed the photon background because in 1948 neutrinos were only just becoming understood as particles. The paper describing neutrinos as distinct particles from electrons, the paper establishing the properties that would eventually allow the neutrino background to be predicted and calculated, had not yet been fully worked out. Alpher was working at the frontier of what was known, and the frontier was already narrow enough. He did what could be done with what was known. He got the right order of magnitude. He pointed in the right direction. He said, "Look here, with an instrument sensitive to this range of frequencies, and you will find the echo of the beginning." Nobody looked. It took 16 years and a pair of radio astronomers trying to calibrate a 20-foot horn antenna and a nest of pigeons inside it before anyone found what he had described. This is not a tragedy in the literary sense. It is not structured as a tragedy. Alpher lived a long life. He had a productive career. He received recognition delayed, partial, insufficient by some measures, but real. He received the National Medal of Science. He gave lectures. He wrote papers into his 80s. He collaborated with colleagues he respected and who respected him. He was not, as far as any record shows, broken by the recognition question. He was something more specific and harder to name, a man who had been shaped by a specific experience, who had organized his professional identity around a precise account of what had happened and who had done what, and who maintained that account with a discipline that suggested the effort required to maintain it. The discipline is the thing. The precision in the interviews is the thing. The way he said he was not bitter, and the way it sounded like the thing he had decided to say. These are not dramatic details. They are the details of a life that had absorbed a specific weight for a long time and had not collapsed under it, which is neither a triumph nor a tragedy, but is something true. Let me tell you now about the number itself in the context of the future, because the future is where the number is going, and the future is the part of this story that no human alive will see. In approximately 100 trillion years, 10 to the power of 14 years, the last stars will have burned out. The universe will be dark. The cosmic microwave background will still exist. It will have cooled to approximately 2.7 times 10 to the -5th Kelvin, roughly 100,000th of its current temperature, because the universe will be roughly 100,000 times larger than it is today. The photons will still be there. 411 per cubic centimeter will have become something much smaller, spread across a volume much larger, but they will be there, still carrying the signature of the blackbody spectrum, still tracing the Planck curve, only now the curve will peak at wavelengths measured in kilometers rather than millimeters. In approximately 10 to the power of 40 years, the timescale at which protons are predicted to decay, if the leading theories of proton decay are correct, ordinary matter will have ceased to exist. There will be no atoms, No molecules, no planets, no stars, no anything made of protons and neutrons and electrons. There will be photons, neutrinos, black holes, and the vacuum. The cosmic microwave background will still be there. It will have cooled to a temperature so close to zero that writing it as a number requires a string of zeros after the decimal point long enough to fill this paragraph. In approximately 10 to the power of 100 years, the timescale over which black holes evaporate through Hawking radiation, the last black holes will have radiated their mass away as Hawking radiation and disappeared. At this point, the universe will contain nothing but photons, neutrinos, and perhaps gravitons, and the lowest energy states of whatever quantum fields exist. The cosmic microwave background will still be there. It will have cooled to a temperature so far below zero that it might as well be zero, but it is not zero. It is approaching zero along an asymptote. It gets arbitrarily close but never arrives. The universe ends to the extent that end is a meaningful word for something that approaches zero, without reaching it as an expanding void filled with photons of arbitrarily low energy, arbitrarily cold, still following the Planck distribution, still carrying the shape of the spectrum they achieved in the first year of the universe's existence. The signal from the beginning, written into the shape of that curve, persists into the infinite future. The shape of the distribution is indestructible. As the temperature falls toward zero, the curve shrinks and shifts but never distorts. The physics of the first seconds is preserved in the structure of the radiation until the structure itself loses meaning. This is what Alpher's calculation was about. Not just the present temperature, the entire thermal history past and future of the radiation field that fills the universe. He did not calculate the far future explicitly. He calculated the present from the past. But the equation he used, the relationship between temperature and scale factor, derived from Friedmann's equations, and the thermodynamics of radiation. That equation contains the future as well as the past. Every solution of the equation is a different cosmological history. The solution that matches our universe, with its specific matter content and expansion rate, gives 2.7255 Kelvin today, and a lower temperature tomorrow, and a lower temperature still in 100 trillion years. The number is a point on a curve that Alpher plotted in 1948. Let me return to 1978, because 1978 is where the accounting becomes undeniable. The Nobel Prize in Physics for 1978 was announced in October of that year. Penzias and Wilson received it for the discovery of the cosmic microwave background radiation. The Nobel Committee's announcement described the discovery as one of the greatest in the history of astronomy. The press releases emphasized the accidental nature of the finding, the antenna, the pigeons, the noise that would not go away. This is the story that has been told since 1965, and it has lost nothing in the retelling. It is a genuinely good story. Accident, precision, the universe announcing itself through a hiss that two careful scientists refuse to explain away. But inside that story, underneath the pigeons and the Nobel Prize and the standing ovation for the COBE data, is the other story, which has a different texture and a different weight, and which is mostly told in the footnotes of papers and the later chapters of physics histories, written by people who felt the obligation to look at the full record. The Nobel Committee knew about Alpher and Hermann. There is no question about this. The prediction was documented. The papers existed. The history had been written about. By 1978, there had been articles and interviews in which Alpher had laid out the record precisely. The committee made a choice about what to recognize and what not to recognize, and their reasoning, to the extent it is knowable, seems to have been that the prize should go to the observation rather than the theoretical prediction, and that the theoretical framework was too entangled with Gamo's work to be cleanly attributed. This is a defensible position. It is not the only defensible position. The committee had options. The committee chose. What it cost to choose this way is not a number you can calculate. It is distributed across decades of interviews and conference talks and papers in which Alpher and Hermann documented the record with increasing explicitness as they got older, and the time available to document it grew shorter. It is in the specific wording Alpher used when he said he was not bitter. It is in the standing ovation for the COBE data that Alpher may or may not have heard about in a conference room in New York, and which was for the precision measurement of a number he had first estimated in a small office in Washington, D.C. in 1948. 2.7255 Kelvin. That number is the temperature of the universe. It is in the title of this script, and it is in the calculation Alpher did, and it is in the COBE data that made the audience stand up, and it is in the Planck satellite results published in 2018, which produced the most precise measurement of the cosmic microwave background spectrum and temperature anisotropies ever made. The Planck results are the current state of our knowledge. They constrain the age of the universe, the Hubble constant, the density of dark matter, the density of dark energy, and the spectral index of primordial density. Fluctuations, a parameter that describes the pattern of the earliest quantum fluctuations in the primordial plasma, the original seeds of all structure. Every one of these constraints flows from the measurement of the background radiation. Every one of them sits, in some chain of reasoning, on the foundation that Alpher laid. Now I want to talk about what happens to the number in the very near future, because the near future is where the story gets strange in a different way. The universe is not just expanding, it is accelerating. This was discovered in 1998, when two independent teams of astronomers, the High Z Supernova Search Team and the Supernova Cosmology Project, measured the distances and recession velocities of very distant supernovae and found that they were receding faster than expected. The universe's expansion is not slowing down due to gravity, it is speeding up. Something is driving the acceleration. That something is called dark energy, and it constitutes approximately 68% of the total energy content of the universe, and we have essentially no idea what it is. The discovery of dark energy changed the future of the cosmic microwave background in a specific way. If the universe's expansion is accelerating, then the rate at which the cosmic microwave background temperature falls will itself change over time. In a universe with no dark energy, the expansion would slow gradually, and the temperature would fall at a rate that also slows gradually. In a universe with dark energy in our universe, the expansion accelerates, and therefore the rate of temperature decrease also accelerates over very long timescales. The universe cools faster than it would have without dark energy. This is not a large effect on the timescales of human civilization or even of stellar evolution, but on the vast timescales of the universe's future, it changes the curve. The asymptotic approach to zero happens faster, and there is another consequence of dark energy that is stranger than accelerated cooling. In approximately 150 billion years, roughly 10 times the current age of the universe, the expansion of the universe will have accelerated to the point where galaxies outside our local group will be receding faster than the speed of light. Not because anything is moving faster than light, the expansion of space itself is not constrained by the speed of light in the same way, but because the space between us and distant galaxies will be growing faster than light can cross it. At that point, those galaxies will pass beyond our cosmic horizon. They will be causally disconnected from us. We will not be able to see them, communicate with them, or be affected by them in any way. What this means for the cosmic microwave background is that the photons we see today, coming from the surface of last scattering 13.8 billion light-years away, will eventually be the oldest photons in our observable universe, in a different sense, not the oldest that exist, but the oldest that we can ever detect, because as the universe accelerates, the surface of last scattering itself will slip beyond our horizon. Eventually, an observer in our galaxy in the far future will see no cosmic microwave background at all. The photons will still exist. They will be passing through everything. But they will be so cold and so long wavelength that no conceivable instrument could detect them. And the observable universe will appear to be not the remnant of a Big Bang, but an island of galaxies in an empty void, with no evidence of origin and no light from the beginning. Future astronomers, if they exist, will not know they live in a universe that began. This was pointed out in a paper published in 2007 by Lawrence Krauss and Robert Scherer, and it has a specific resonance in the context of this story. The observational evidence for the Big Bang, the cosmic microwave background, is not permanent. It is present now because we live at the right moment in the universe's history, when the light from the beginning is still detectable. We live in what Krauss and Scherer called the golden age of cosmology, not because our instruments are best, but because the universe has not yet hidden its origin from us. The background radiation is still here. The temperature is still measurable. The number still exists. 2.7255 Kelvin. Ralph Alpher said it should be approximately 5 Kelvin in 1948. He did not know about dark energy, no one did. He did not know about the acceleration of the expansion. He was working with the best cosmological data available, and a physical framework that was, at that point, contested by a significant fraction of the physics community. He derived the prediction from first principles, from the thermodynamics of the expanding universe, from the nuclear physics of the early plasma, and he got it right to within a factor of 2. He published it. He talked about it. He waited. He waited a long time. In 1993, Alpher and Herman published Genesis of the Big Bang, a book they had co-authored over many years, documenting the history of their work on nucleosynthesis and the prediction of the background radiation. It is a careful book. It is precise. It covers the physics in detail and the history in detail, and it makes the case, with documentation, for the priority of their prediction. It was reviewed respectfully. It was not widely read. It is out of print now and difficult to find. There is a copy in the library at Union College in Schenectady, where Alpher spent part of his later career. I want to talk about what Alpher's calculation actually required, because the difficulty of it is part of the story, and it is part of what gets lost when the prediction is reduced to a single line in a history of cosmology. Alpher's dissertation addressed Big Bang nucleosynthesis, the process by which the light elements were formed in the first few minutes of the universe. This meant he had to model the early universe dynamically, not as a static object but as a process unfolding in time, with temperature and density changing continuously as the universe expanded. He needed to track the relative abundances of neutrons, protons, deuterium, helium, and heavier nuclei as the universe cooled and the nuclear reactions proceeded. Each reaction had a rate that depended on the temperature and density. The rates changed as the temperature changed. The abundances changed as the rates changed. The temperature changed as the universe expanded. Everything was coupled to everything else, and the coupling was nonlinear, and there were no computers. Alpher built what was, in effect, a numerical integration of the system of coupled differential equations governing the evolution of the early universe. He did this with a mechanical calculator, the kind of device that could do arithmetic operations one at a time, by turning a crank or pressing keys, and which required the user to write down intermediate results and feed them back in manually. He worked through the system step by step, advancing time in small increments, updating the abundances and temperature at each step, recording the results. The calculation filled hundreds of pages. It took months. And embedded in this calculation as a necessary component of tracking how the temperature evolved was the relationship between temperature and scale factor that, extrapolated to the present age of the universe, gave the background radiation temperature. This is not a side result. It is not an incidental observation that emerged from the main calculation. It is built into the structure of the problem. You cannot calculate Big Bang nucleosynthesis without tracking the temperature. And if you are tracking the temperature from the first seconds to the present, you are calculating the temperature of the background radiation. Alpher did not have to make an additional effort to find the prediction. The prediction was in the calculation he was already doing. It emerged from the mathematics as a consequence of the physics. This is what makes the attribution question sharp in a way that it is sometimes blunted. Alpher did not, in some sense, predict the cosmic microwave background as a separate act. He predicted it as a necessary consequence of the calculation that was his dissertation. The calculation was his. The prediction was the calculation's output. The output belongs to the person who did the calculation. In 1956, a radio astronomer named Edward Ohm, working at Bell Labs, the same institution where Penzias and Wilson would work 8 years later, made measurements with a large horn antenna at Crawford Hill, New Jersey, not far from the site where Penzias and Wilson would eventually make their discovery. Ohm was characterizing the noise properties of the antenna system for communication purposes. He measured the total noise temperature of the system, the sum of all noise contributions from the electronics, the atmosphere, and the sky, and found a small excess that he could not account for. The excess was approximately 3.3 Kelvin above what his models predicted. He noted this in his paper. He did not know what it was. He attributed it to instrumental uncertainty. He moved on. He had measured the cosmic microwave background 8 years before Penzias and Wilson. He had the number. He had the antenna. He had the data. He did not know what he had. This is the other face of the story, the one that complements Alpher's. Alpher had the theory and did not have the experimental confirmation. Ohm had the experimental signal and did not have the theoretical framework to recognize it. The theory and the observation existed simultaneously for 8 years without finding each other. In 1964, they found each other not through any deliberate effort to connect them, but because Penzias and Wilson's persistence with a noise they could not explain eventually led to a phone call to Dick's group at Princeton, who had the framework, and the two pieces came together. The symmetry of this is clean enough to be suspicious. Both the theory and the observation were sitting unrecognized for years. Both were found again independently. Both convergences happened at almost the same time. The theory was rederived by Dick in 1964. The observation was made again by Penzias and Wilson in 1964. They met in 1964. The meeting produced a Nobel Prize. The earlier version of both the theory and the observation, Alpher's prediction and Ohm's measurement, produced a footnote in a history that mostly gets told without them. There is a word for this kind of coincidence in the history of science. Simultaneous discovery, the phenomenon in which the same idea is developed independently by multiple people at approximately the same time, is well documented. Newton and Leibniz and calculus, Darwin and Wallace and natural selection, Bell and Gray and the telephone. Science writers often invoke this phenomenon to suggest that ideas are somehow in the air when the time is right, that the culture and the technology and the available data create conditions that make certain discoveries almost inevitable. This is partly true and partly a comforting story. It papers over the question of what happens to the first person who got there. What happened to Ralph Alpher is not the cleanest story about this. He was not simply beaten to a discovery by a simultaneous independent discoverer. The structure is more complicated. He made the prediction. The prediction was correct. No one followed up on it. The prediction was rederived independently 16 years later. The people who rederived it did not know his prediction existed. The people who made the observation did not know either prediction existed. The Nobel Committee knew all of it and gave the prize to the observers. Alpher lived for 29 years after the prize was announced. He received the National Medal of Science at age 80. The specific weight of that timeline is not something you can convert into a dramatic statement. It is too distributed. It lives in too many small moments over too many years. It is the weight of being the first person in history to estimate the temperature of the universe and spending the rest of your career explaining this in interviews to people who have never heard of you. 2.7255 Kelvin. That is the temperature right now. In 1 second it will be 2.7255 Kelvin, minus 2.3 times 10 to the minus 18 Kelvin. In 1 year it will be smaller by about 7 times 10 to the negative 11 Kelvin. In a billion years it will be smaller by roughly 7 times 10 to the negative 2 Kelvin, measurably smaller, by a few hundredths of a degree, detectable by an instrument sensitive enough to notice. In 10 billion years it will be smaller, by perhaps half a degree. In 100 billion years, as dark energy accelerates the expansion further, the temperature will be approaching 1 Kelvin. The falling never stops. The number always moves in one direction. The universe does not warm. It does not stabilize at some equilibrium. The expansion continues, and the expansion is accelerating, and the temperature falls, and the falling is as close to a law of physics as anything we know, not a tendency, not a general pattern, but a specific quantitative consequence of general relativity and thermodynamics and the initial conditions of the Big Bang, all of which Alpher's calculation incorporated in 1948. The number will be smaller tomorrow than it is today. It will be smaller in a year than it is now. It will be smaller in a century and a millennium and a billion years and a trillion years. It will be smaller forever. There is no version of this universe, under the physics we understand, in which the temperature of the cosmic microwave background increases. The entropy of the universe increases. The space between galaxies increases. The wavelength of the background photons increases. The temperature decreases. This is not a prediction about the future. This is a description of what is happening right now, in every second, without pause. When Alpher did the calculation in 1948, he was computing a present temperature from a past history. But the equation he used is symmetric in time. You can run it forward as well as backward. Run it backward, and you get the temperature at any point in the past. Run it forward, and you get the temperature at any point in the future. The equation does not care which direction you go. It gives you the number either way. Alpher ran it forward to the present and got 5 Kelvin. The present value is 2.7255 Kelvin. The direction he was looking toward, a warm, detectable, measurable signal in the present, was correct. The number was approximately right. The physics was right. The prediction was right. Nobody looked. And when they looked, 16 years later, and found what he had described, the finding was named a discovery, and given a prize, and put in every textbook. And the prior calculation, the one that said, "Look here, this is what you will find," was credited to Gamow, who had provided the framework, but not done the calculation, and cited in the footnotes, where it remains. There is a version of this story in which that is simply how science works. Priority matters less than confirmation. The observer who makes the measurement takes precedence over the theorist who predicted it. The Nobel Committee followed its own rules with its own logic. This version is true in the narrow sense that all those things are accurate descriptions of what happened. Science does work this way. The Nobel Committee did follow its logic. Penzias and Wilson did make a genuine discovery. The version of this story in which that is simply how science works is also the version that costs nothing. It is the clean version, the version without remainder, the version that accounts for everything except the specific life of a specific man who spent 57 years between the calculation and the medal. That gap is not contained in any description of how science works. It is not a systemic failure or a deliberate wrong. It is what a gap between being right and being recognized actually looks like, distributed across a human life, carried with discipline and precision by a man who had decided to maintain an exact account of what happened and who had done what. He maintained that account for 57 years. He maintained it until there was no one left to give it to. The universe maintained its temperature for 13.8 billion years and is carrying it forward, falling by an imperceptible amount in every second, preserving in the shape of its spectrum the physics of the first year of its existence, readable by anyone with an instrument sensitive enough to look. Both things are true simultaneously. The universe is getting colder. The number proves it. The number was first predicted by Ralph Alpher in 1948, and the temperature of the universe was approximately 5 Kelvin then, and it is 2.7255 Kelvin now, and it will be slightly colder tomorrow, and the direction of that change was never in doubt once Alpher had done the calculation, and it will never reverse, and the calculation was correct, and the man who did it waited 57 years for the world to say so. 2.7255 Kelvin. Falling every second, without exception, without end. The number does not care who calculated it first. The universe does not maintain a record of priority. The photons do not remember whose dissertation predicted them. They just travel. They just cool. They fill every cubic centimeter of space with 411 of themselves, and they carry the temperature of the first clear moment of the universe, and they will be carrying it long after the last star has gone dark and the last proton has decayed and the last black hole has evaporated, and the only things left in the universe are themselves. The light from the beginning is still here. It is 2.7255 degrees above the coldest possible thing, and it is falling.